Assalamualaikum, very good morning.
Good morning, Doctor.
Okay, so we're going to continue our lecture on chapter 7, which is the last lecture for our syllabus. Last chapter for our syllabus. We are supposed to have two parts for lecture 11, which are actually the lectures. I think say this is last lectures, lecture 11 will be the last lecture. Comprises of two parts, part 1 and part 2. So for today, we're going to cover part 1. Okay, and inshallah on next week, we're going to finish part 2, which will wrap up the syllabus of our course. Yeah. Okay. For chapter 7, the topic, so the title for this chapter is Optical System Design. Okay, that should be the big title for chapter 7. But the main things to be discussed in this chapter 7 for today's lecture will be the power budget. Yeah, power budget. That should be the topics to be discussed today. Right. So this will be the content of today's lecture. We're going to cover the introduction to optical system design. Yeah, what is the purpose of having optical system design? And number 2, we're going to have a look at the power budget analysis. Okay, and we compare this with the CI, from the CI. So this is the essence, the things that we accept from the CI, we have the topics of optical system design using power budget and rise time budget analysis. So basically, for chapter 7, we're going to have a system design based on two techniques or two analysis. The first one is power budget. Yeah, that should be the first one we're going to cover today. And next week, we're going to finish the second type of analysis, which is the rise time budget. Yeah. So there should be two analyses to be covered in this chapter 7. Okay, about the new generation of optical fiber network. I think I'm not going to cover this because you can just go through any references, any information that you can obtain it from the internet. Yeah. Okay, so our syllabus will be end up until these topics of optical system design only. Yeah. Okay, so let us proceed with the optical transmission. I believe that these are the topologies, network topologies that we have learned, I believe, in third year SEM 2 last semester. The data communication, data communication. Yeah, I believe we have been taught about this topology of a networks. Yeah, topology of networks. So basically, we have two types of transmission. The first one is a link transmission. Yeah, this is the easiest one. Link transmission, which is one point to point. Yeah, we have a point A, we have a point B. Yeah, so this is point to point transmission, right? And this transmission do involve a fiber optics. Yeah, fiber optics will be required in your transmission. Okay, it's understood. And then we have a network transmission. There are a few types. We have the bus transmission, bus topology. We have the star topology, we have a ring topology, and so on, also the tree and the mesh topology. So all of these computers, so all of these networks are actually interconnected by using fiber optics. Yeah. So it's very important for us to have a proper design, proper design of optical system transmission, such that the power transmitted will be safely received. I can say safely received, or in other words, I can say the amount of power received at the receiver is enough. Okay, so that should be the best word to be used. The power transmitted by the source, at the transmitter side, should be then received at the receiver side. In which the amount of power received is enough. It's enough to be recovered. By the receiver. Or by the detector. So these are the things that motivate us to learn about or to cover these topics of optical system design. Okay, right. So these are the elements, the elements of a link or elements of network that are very important in our optical system design. So basically I can say these are the parameters, yeah, the parameters that will involve in our optical design or optical system design, yeah, in which we know that from what we have learned last time, very first lecture of this course, we have learned that a basic optical communication will comprise of three elements. We have the transmitter, okay, we have receiver, and in between we have the channel, right? Okay, we have the channel. So basically, our system will comprise of these three important things: the transmitter, the receiver, and the channel. So basically, in our optical system design, we have to consider the effect of our transmitter, the effect of our receiver, and the effect of our channel. So in our case, the channel is optical fiber. Okay, so I did mention here the elements or the factors that will involve in our optical design. We have the fiber type, yeah, so we can use either a single mode or a multi-mode. Okay, so and also I can relate this with your assignment that you have to do, yeah, you have to do basically, because it's more towards the, basically your assignment is on optical system design, yeah, so you have to carefully select what should be the proper transmitter to be used, what should be the proper receiver to be used, yeah, I mean, you need to use, whether you want to use LED or you want to use a laser diode for the transmitter, or for the case of receiver, whether you want to use the pin photodiode or you want to use the APD, yeah, or for the case of fiber optics cable, whether you want to use the single mode, you want to use a multi-mode, or maybe you want to use a step index or gradient index. So these are the possibilities, yeah, possibilities that you have to consider in your design, apart from the factors of financial factors, yeah, or economic factors. So these are the things that need to be considered in your solution, yeah, of the assignment. Yeah. Okay. So back to this. So the factors that will involve may be the fiber, yeah, the fiber. So you have to choose either to use a single mode, multi-mode. The wavelength used, yeah, whether you want to use 850, 1310, or 1550 nanometer. Okay, and you have to depends on the attenuation, yeah, that will actually incurred, yeah, in this wavelength that you want to use, yeah. So you have to consider all of these factors, okay. And transmitter power, yeah, what is the transmitted power that you want to send, yeah, throughout the fiber optic channel. The laser, the source type, whether you want to use a laser or LED, okay, the selection of this. And then the receiver's sensitivity, okay, what should be the amount of the lowest, the smallest power of, the smallest power that can be received, yeah, that can be recovered by the receiver. So this is what we call as receiver sensitivity. So for instance, if you, let's say your receiver sensitivity is a negative, for example, let's say, yeah, it's a negative 45 dBm, for instance, yeah. Let's say this is your receiver sensitivity. And then the send, I mean the receive value, yeah, the receive value at your receiver side is smaller than this, yeah, smaller than the sensitivity of receiver. Let's say, for example, it's negative 47. So in this particular case, if I have a value of receive power which is smaller than the receiver sensitivity, the result will be this particular signal cannot be recovered by the receiver. Okay, yeah? So it's very important then to have a proper optical design in your work. Yeah. Okay, so the same things applied for the case of a detector. You may use the pin photodiode, yeah, or you may use the APD photodiode. Yeah. So these are the photodiode type that we have learned in chapter 5 and also in chapter 6. Yeah, when we considered noise in optical receivers. Yeah. Okay. And this is about the systems, yeah, the systems. This is more towards the code, modulation code, whether you want to use the EM, FM, PCM. So this is more towards the systems itself, yeah. Whether you want to use a AM, FM, PCM, or digital modulation code. Yeah, whether you want to use the RZ, the no return to zero, then RZ, and just the coding and so on. Yeah. Okay, and for the bit error rate, you have to choose either you want to use 10 of -9, 10 of -12, which is depending on your signal to noise ratio, yeah, that you want to maintain in your system, yeah, because bit error rate and SNR is interrelated, yeah. Okay, so we have the signal to noise ratio down here. So number of connectors need to be considered in your systems, yeah, number of splices. So these are the things that need to be considered in your optical system design later on, yeah, and also about the environmental requirements, yeah, what should be the whether your application can be exposed to high temperature or can be exposed to sunlight, yeah, what should be the humidity level that allowed, yeah, in your installation or fiber installation, for example, yeah, and also related to these mechanical requirements, whether your optical fiber, is it for the indoor or for the outdoor application. So these are the things that need to be considered in your design later on, yeah. Okay, right, so I can say the next slide is related to what we have discussed in chapter 3, yeah, chapter 3, sorry, chapter 4, I believe, on the optical sources. Yeah, so these are the topics that we have learned on the laser diode and the LEDs, yeah, which include the output power, the bandwidth, the central wavelength, the line width, yeah, the spectral width, the number of modes. So these are the things that we have learned, yeah, in chapter 4 before. Okay, so you need to apply all of these knowledge that you have learned in the previous chapters, of this course in these particular topics of optical system design. Yeah. Okay. Right. And also about the fiber optics itself, the channel, which is covered in chapter 2 and chapter 3. Okay. We have been taught. We have learned about the type of fiber optics, a single mode fiber, the multi-mode fiber. Yeah. What should be the effect on the attenuation? What should be the effect of a dispersion? Yeah, the chromatic dispersion, the numerical aperture, the cutoff wavelength. So these are the things that we have learned previously in chapter 2 and chapter 3. So I hope that you can still recall of this information, because later when you go out to work, yeah, in case if we have a chance to work in this field of optical communication design, yeah, so it will be very good for you then, yeah, because you have all of these fundamental knowledge, yeah, on these fiber optics, on the transmitters, on the receivers, and also on these on system design configuration. So it's very important then, yeah. So it's good if you can apply all of the knowledge that you have learned in this course when you go out to work later on, yeah. Okay, and about the photodiode, this is what we have learned in lecture chapter 5 and 6, yeah. So we have been taught about the bandwidth, yeah, the bandwidth, the wavelength range, yeah, the response wavelength range, and also this beam detection level. So basically, this is about the sensitivity, yeah, sensitivity. Okay, I'm not sure what happened with this with my tab here, yeah, it keep on giving the lines. I'm very sorry about this, yeah, it's quite is very much disturbed, yeah, our teaching and learning. I'm very sorry about this, out of my control basically. Okay, all right, so let us proceed with this optical link loss budget, which is the actual topics to be covered in chapter 7. Okay, so basically the link loss budget, yeah, optical link loss budget will be the key calculation in designing a simple fiber optic link. Okay, so it's very important for us to understand this link loss budget. So the objective of this link loss budget is to determine the launch power and also the receiver sensitivity. Okay, so whether the launch power that we introduce in the system, is it is it enough? Yeah, is it enough to be recovered at the receiver side? Okay, and basically it will involve the value of the receiver sensitivity. Okay, so all of these is interrelated. Yeah, when you start the optical system, when you proceed with the optical system design later on. Yeah, so there should be two types of optical link budget calculation. The first one, which will be covered today, will be a calculation of loss budget or link budget based on the power transmitted. So yeah, based power transmitted, the PTX, based on the power received. So we need to have this information in the power received, so the PRX, yeah, the PRX, and then need to find out what should be the value of attenuation or loss induced by the fiber itself, yeah, the loss induced by the connectors, loss induced by the splices, and the loss induced by the dispersion. So these are the information that need to be obtained before you can start designing the optical system using this analysis of power budget. Okay, so we're going to see in our example later on how this power budget analysis can be used in designing our optical system. Yeah. Okay, and for our lectures next week, which will be based on the rise time budget. Okay, rise time budget. It should be based on calculation, in which from the name implies, you're going to understand or going to know what should be the value of the rise time value of the source or the transmitter. It will depends on the value of fiber dispersion, and it will depends on the rise time value of your detectors, and your amplifiers. So yeah, so this will be learned later next week. Yeah, about the second method of link budget, which is a rise time budget analysis. Yeah, so our concern will be the first one for today, which will be on the power budget analysis. Okay, let's proceed with the number one, which is the power budget. All right, so the important things in power budget will be two things, which is the power transmit and the power receive. Yeah, power transmit and power receive. Yeah, which is I can say this will be the amount of acceptable loss. Yeah, the amount of acceptable loss. For instance, if you send at the receiver, the PTX, for instance, is let's say a 0 dBm, for instance. Yeah, 0 dBm, and at receiver side, yeah, the receiver sensitivity is let's say negative 40 dBm. Yeah, 40 dBm. So we have a difference between the input and output value. Yeah, in terms of a dB will be a 40 dB. Sorry, yeah, 40 dB. Yeah, 40 dB difference between the input power and receive power, 40 dB. So it means that this 40 dB will be the allowed, yeah, will be the allowed loss, yeah, allowed loss in your system, which are said to be incurred maybe by the fiber itself, maybe incurred by the connectors, the splices, for instance, or maybe due to the attenuation. Yeah, so this will be the allowed value of attenuation or loss in your channel. Okay, yeah. So basically, if for instance you manage to get the value of the difference between the input, yeah. For instance, if you have a 0 dBm here, the transmit is 0 dBm, and at receive side, the value, for instance, is negative. For instance, it is a negative 30 dBm. Yeah, so it means that the signals can be recovered. Yeah, can be recovered at the receiver side. Yeah. Okay. So this power budget analysis will involve power calculation from the transmitter to the receiver, as I mentioned before, and these are the factors that need to be considered. Yeah, in your in between the transmitter and receiver, we have the attenuation. Yeah, we have the coupled power to the fiber optics. We have the SNR requirement. We have the minimum power at detector, which is the receiver sensitivity. We have also the bit error rate. Yeah, so this is the things that need to be considered in your design. Yeah, and then we have the channel loss due to the connectors or splices. So we normally use a CL here to represent the channel loss due to these connectors and splices. We also have a safety margin, yeah, safety margin, and we also have the dispersion equalization. So what is meant by safety margin and dispersion equalization? So we're going to discuss this later on, yeah, in our slides, yeah. Okay, so this will be the equation that will be used in our optical power budget calculation, where the PR here is the minimum or the mean input power launched into the fiber. So that should be the PI. I can say also we normally use a PTX, yeah, which is transmit power. The P naught here is your minimum, the mean optical power at the receiver, yeah, mean optical power required at the receiver. So we're going to use a PRX, yeah, PRX, and then we have the CL, yeah, CL will be your channel loss due to the splices. We have the MA, which is system margin, and we have the DL, which is the dispersion equalization. So basically, for your optical power budget calculation, the transmit power, yeah, must be at least, yeah, must be at least equal to the summation of these factors. Yeah, so I repeat again. For power budget calculation, yeah, for proper system design, your transmit power, yeah, your transmitted power shall be at least equal to the summation of these components, yeah, which include the receive power, the channel loss, the system margin, and the dispersion equalization value. Yeah, so that should be the minimum requirement to ensure proper optical system design in which the transmit power must be at least equal to the summation of these components. Okay, yeah, so I hope that you are very much clear about this explanation on the power budget analysis. Okay, so let us proceed with the BR calculation, which is the interrelation between the BR and the SNR. Okay, sensitivity of the detector is the minimum detectable power. Okay, so we have discussed this before. Yeah, sensitivity of detector is a minimum detectable power. For instance, if your detector is having a sensitivity of negative 45 dBm, okay, so basically this will be the minimum, yeah, the minimum detectable power of your receiver, which means that if your the receive power is less than this, so we cannot recover the signal. Yeah, we cannot recover the signal. Okay, so it is the definition of the sensitivity of detector is basically the minimum required power to achieve certain SNR or BR. Yeah, so that should be the sensitivity. Yeah, because if we have smaller than this amount, so we cannot achieve the stated or the proposed SNR or BR of the system. Yeah. Okay, so in order to determine whether a detector is suitable for a link, sensitivity must be less than the power received at the detector. So which means that the power received must be bigger than the sensitivity. Yeah, so that's why I mentioned before. If your sensitivity is negative 45 dBm, so the received power at the receiver must be bigger than this amount. Yeah, such that the systems can work properly. Yeah, or it can achieve the required or the certain value of SNR or BR that has been proposed earlier. Okay, so this will be the equation of BR. So PE is a probability of error calculation, or we also consider this as a BR. So BR, which is a probability of error calculation, is given by this equation, half of ERFC. ERFC stands for the complementary error function. So this error function, we have the SNR, power of or square root of SNR divided by 2 square root of 2. So this is the equation that relates the BER. Yeah, this is our BER. Okay, that's our BER and the SNR value. Okay, and it related by this error complementary error function, the ERFC. So basically, you can find out the ERFC value from your, from the computers. Yeah, from the Google. Yeah, from Google, you can find out, let's say, if we have ERFC, for instance, equals to 4.24. So the value for this will be equals to about almost equals to 2 times 10 power of negative 9, which is given these examples down here. Yeah, you can check using you can Google this value, yeah, ERFC of 4.24. So if you calculate ERFC of 4.5, you're going to get a really different value for this ERFC for 4.5, yeah. Okay, so for this example, in which I show you the how relation between the BER and the SNR. For instance, if your BER is 10 power of negative 9, yeah, that should be the value of BER. So we know that from this equation, yeah, when the BER is 10 of power negative 9, so 2 can be brought to the left hand side. So we're going to have 2 times power negative 9. So that will left us with ERFC of SNR, square root of SNR divided by 2 power of 2 times square root of 2. So from the Google, yeah, from this ERFC value that you can find from the Google, you're going to have the ERFC, this means 2 times 10 power negative 9 shall be equals to ERFC of 4.24, yeah, about, yeah, okay, about that values, yeah. So which means that the SNR value in this bracket is equals to 4.24 as mentioned here, yeah, and from here you can find out that SNR will be equals to this value in linear form, and in dB it is 21.6 dB. Okay, so for the BER of 10 of negative 9, your SNR is 21.6 dB. Yeah. So this is just the example on how we can relate the BER and the SNR, which is obtained from these equations here. Okay. All right. And what is system margin? Okay, system margin basically can be expressed by this equation. Yeah, by this equation in which we have the MA. We have this MA. MA stands for the system margin. Will be equals to the transmit power minus the receive power minus the system loss. Okay, yeah. So when we calculate, let's say, the value of the power transmit minus the power received minus system loss, if the results of the subtraction on the right hand side, if the value is positive, yeah, if the value of positive, means that the system margin that we have in our calculation here will ensure proper operation of the optical system. Yeah, means that if the result of the subtraction is positive, means that the system that we are designing will be working in a proper condition. Yeah, but if the results of the right hand side subtraction is negative, yeah, it's negative, it means that we are going to have insufficient power that will reach the detector to achieve the required BR or required SNR. Okay, so for the case of a negative value of system margin, the system cannot work properly and we have to redesign the optical system. Okay, so you have to ensure that your system margin will always or must always be positive so that the systems will work properly. Yeah, so that's why I mentioned here that in our system design, you always want a positive value of system margin. Yeah. Okay. Next is about dispersion equalization that we have mentioned in our equation of this one. Yeah, the public calculation. We have this DL down here. Okay, this is DL. So what's the dispersion equalization? Okay. So basically, this is we know that from what we have learned in chapter 3, when we learn about the fiber optic itself, we have the effect of dispersion, right? That is occurred majorly, yeah, mostly in our multimode fiber, yeah, multimode fiber dispersion effect. Okay, so basically you need to introduce this dispersion equalization, yeah, such that we can compensate, yeah, we can compensate for these dispersion effect. Yeah, so I did mention here that when we have a dispersion, yeah, when having dispersion, we are going to have the additional loss, which is contributed by the intersymbol interference. Yeah, so we have learned about this intersymbol interference before in chapter 3. Okay, so we have when we have a dispersion, yeah, the pulse dispersion that occurred in the fiber optics cable during the transmission of the signal will then result on the overlapping of the received pulses. So it is understood, yeah. So when we have a dispersion, the pulse will be overlap. Yeah, the pulses will be overlap, and the overlap of these pulses will lead to the ISI, the intersymbol interference, and this will further result on the reduction of the optical receiver sensitivity. Okay, so this is a chain reaction, yeah, a chain reaction. So when you have a dispersion, will create the ISI, and when you have the SI, will reduce the receiver's sensitivity. So that's why, yeah, that is why we need to consider the effect of dispersion here by introducing what we call as a compensation, yeah, compensation, or I can say equalization, yeah, compensation of this ISI effect by the method of equalization within the receiver. And that is why we need to introduce this kind of dispersion equalization in our system design, yeah, in which this will be the introduction of optical power at the receiver, in which we consider this as additional loss penalty. Yeah, additional loss penalty. So basically, we want this DL to be as small as possible. Yeah, we want the DL to be as small as possible because this is a penalty, so we don't want it. Yeah, we don't want it. But as long as we have a dispersion in our fiber optics, so this DL need to be considered. Yeah, it need to be considered. Yeah, so that is why we consider the loss penalty here to be known as a dispersion equalization of ISI, or also known as a DL. Yeah, in DB unit. Yeah. Okay then. Yeah, so I hope by now you understand what is meant by the safety margin, the MA. You understand what is meant by the DL. Okay, and channel loss is very common. Yeah, channel loss is the loss due to the fiber optic itself, the loss due to the connectors, and the loss due to the split splices. Yeah. Okay. Right. Any questions up to now before we proceed with these examples on the power budget analysis? No.
No, Doctor.
Okay, if there's no question, I think we can now proceed with the example on the power budget analysis, just to ensure that you really understand about these issues of power budget analysis. Yeah? Okay, so in this example number 1, we need to make a comparison by calculating the maximum attenuation limited transmission distance of the following two systems operating at 100 megabit per second. In this particular case, we are allowing a 6 dB system margin. Yeah. Okay. So we are having two systems. The first system is operating at 850 nanometer. The second system is operating at 1300 nanometer, and it has its own transmitter and receiver. I also have the fiber optics type and also the information about connector loss. Yeah. The same thing is applied for the second system. For the first system, we are using the laser diode. Yeah, we are using the APD, using the green fiber, okay, with the given specification. For the system 2, we are using the LED, using the pin photodiode and the green fiber used. Yeah. Okay. So in these questions, we need to calculate the maximum attenuation limited transmission distance. So in other words, we need to find out what should be the maximum transmission distance allowed by this system. Yeah. So we need to use L. Yeah, we can write L as a distance allowed for both cases. Yeah, we have L for both cases, right? So we need to find out what should be the L value. Yeah, L value. So let's say I'm using L1 for system 1 and I'm using L2 for system number 2. So we need to compare between these two systems, what should be the amount of L1 and what should be the amount of L2. So L1 and L2, both of them are the allowed transmission distance if you are using this kind of configuration of your optical systems. Yeah. Okay, let's have a look at the solution for this example. Okay, please recall that the system number 1 is using this information. Yeah, 0 dBm of power, couple power. The APD is having negative 50 dBm sensitivity. Okay, so this should be the smallest value of power that can be received at the receiver. The loss induced by the green fiber is 3.5 dB per kilometer attenuation at 850 nanometer, and the loss of connectors is 1 dB. So connectors basically should be 2, because connectors will be the connectors at the between the transmitter and the fiber optics. Okay, this is your fiber optics. So we have 2 connectors. The first one is here between your transmitter and receiver. The second one is at the end between the fiber optics and the receiver. Okay, so we have 2 connects basically in our system. Yeah, so supposedly in this particular case, you are having 2 connectors, each for the input and for the output. Yeah. Okay, and for the case of system number 2, at 1300 nanometer, the LED use is having this value of couple power, negative 13 dBm. The pin photodiode sensitivity is negative 38 dBm. At 1300, the attenuation of the green fiber is 1.5 dB per kilometer. Sorry, I need to have a dB here. Yeah, that should be a dB per kilometer. And again, the connector loss is the same as before, which is 1 dB per connector. Yeah. Okay, so let's have a look at the system number 1. Yeah, system number 1 value of L1, or the maximum allowed distance. Okay, so from what we have learned before, from the equation for the power budget, we have the transmitted power must be at least equals to the received power. Okay, sorry. Again, these problems keep on disturbing us. I'm very sorry about this, yeah? I'm very sorry. Okay. So, must be at least equals to the received power plus the channel loss plus the system margin plus the dispersion equalization value, right? Okay, so these are the equation for the link budget analysis or power budget analysis in general. Okay, so in this particular case, since we are not given any information of a DL, we don't have any DL information, so we can ignore the DL. Yeah, we can ignore the DL because no information is given on the DL, so we can ignore the DL straight away. Okay, that can be ignored. Yeah, so this is for system number 1. Yeah, number 1. Okay, so we can write the equation can be written as P transmit minus the P receive shall be equals to the channel loss plus the system margin. Okay, so let us proceed to the left hand side first. You have learned for the system number 1, the transmit power is 0 dBm minus the receive power sensitivity of your receiver is negative 50 dBm. Yeah, so we have negative 50 dBm. Okay, so this is in dBm value. Okay, in dBm value, and equals to the channel loss. Yeah, channel loss is equals to the effect of your fiber attenuation plus the loss induced by the connectors and loss induced by the splicers. Yeah, so in this particular case, your channel loss will be of 2 types or 2 values. The first one is the attenuation of the fiber itself, which is 3.5 dB per kilometer multiply with the L1. Yeah, I use L1 here because we have agreed that the allowed distance for system 1 is L1. Okay, so that should be the loss induced by the fiber itself. Yeah, 3.5 dB per kilometer multiply with the L1 kilometer. Yeah, plus the loss induced by the connectors, which is 1 dB. Yeah, 1 dB per connectors. So since we have 2 connectors, okay, so since 2 connectors, so we're going to have multiply with 2. Okay, why 2? Because we have 2 connectors, one for input and one for output. and plus the system margin, yeah, MA, and as we have informed from the questions, we have 6 dB, yeah, 6 dB of system margin. Okay, so that should be the system margin value. So from here, we can proceed with the equations, yeah. So I'm going to have a 50 here equals to 3.5 of L1 okay, 3.5 of L1 plus 2 dB plus 6 dB, which will give us 8 dB. Okay, so I can just use dB here, right? So from here, we can have the L1 will be equals to 42 divided by 3.5, and this will give us about 12 kilometers for your allowed transmission distance for system number 1. Yeah. Okay. For system number 2, okay, I'm going to use the same equations as above. Okay, same equation. Again, we ignore the dispersion equalization value of the DL because no information is given there. So we only have a component of transmit power, receive power, channel loss, and the system margin. So if we can recall back from the question, system number 2, it is having a negative 13 dBm as your transmitted power minus the received power of a negative 38 dBm. I see. Keep on disturbing. Not sure what is this, yeah? Okay, negative 13 dBm minus negative 38 dBm. Okay, that should be the sorry. Okay, I repeat again. We have a negative 13 dBm minus negative 38 dBm. Okay, so this is in dBm unit. Okay, and that should be equals to the attenuation of fiber, which is 1.5 dB. Yeah, dB per kilometer. What is this? Yeah, I'm sorry. Yeah, I'm very sorry. I'm very sorry. It's quite disturbing. Okay, never mind. Let us proceed. Okay, so we have a 1.5 dB per kilometer. Okay, so we have L2 as a distance, yeah? L2 as a distance, yeah? L2 kilometer. Okay, and we have a 1 dB loss of connectors for 2 connectors. So we're going to have a 1 dB times 2. Yeah, 1 dB times 2. And then we have the system margin of 6 dB, yeah? Okay, so end up we're going to have a 25 dB. Yeah, difference between the receive power and transmit power of 25 dB. And for this, going to have a 1.5 of L2 plus 8 dB. So we're going to have that L2 shall be equals to, equals to 25 minus 18 minus 8, which will be 17. Yeah, divided by, sorry. Okay, need to repeat again here. Sorry about that, yeah. So we have a 1.5 of L2 plus 8 dB. Okay, so end up we're going to have L2 shall be equals to 17 divided by 1.5, and this will give us the length or the distance allowed for system number 2 will be equals to 11.3 kilometers. Okay, so that should be the comparison between the allowed transmission distance between the two systems that given in our question just now. The first system, the L1 has been calculated to be equals to 12 kilometer, while for the system number 2, the L2 allowed, the distance allowed is 11.3 kilometer. Yeah, so that should be the comparison between the distance of these two systems. Right, any questions so far on the solution? Right. Any questions so far?
No, Doctor.
Okay. Right. So let us proceed with this example number 2. We are given a following components available in our system, where we have a gallium arsenide laser diode, within the laser diode, operating at 850 nanometer and capable of coupling 1 milliwatt or 0 dBm into a fiber. Okay, so which means that in this particular case, your laser diode is having 0 dBm input power or couple power. We have a 10 sections of fiber optic cable with 4 dB per kilometer attenuation and has connectors on both ends. Okay, connector loss of 2 dB per connectors. Okay, and we have a pin photodiode receivers and also an avalanche photodiode APD receiver. So these are the given components, available components when we want to design the system. Okay, so by using this component, the engineer wishes to construct a 5-kilometer link operating at 20 megabit per second. Okay, so the distance is 5 kilometers. If the sensitivities of the PIN or the pin and APD receivers are negative 45 dBm and negative 56 dBm respectively, which receiver should be used if a 6 dB system operating margin is required? Okay, so we have to choose either to use a pin photodiode or pin receivers or APD receivers. If the system margin given is 6 dB. Okay, so we have to choose. We have to choose. The idea is you are given all the information, the transmitter value, a couple power of transmitter or laser diode. You have the information of channel loss, channel loss, connector loss, and the options now is to choose which receiver to be used, whether the pin photodiode or the avalanche photodiode with respective sensitivity, negative 45 dBm for the pin and negative 56 dBm for the APD. Okay, so let us proceed with this solution. Okay, but before that, I just want to find out what should be the value of the loss induced by the fiber optics cable here, given that we are having 10 sections of fiber optic cable. So if we can state for you, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 sections there. Okay, 10 sections of fiber optics cable. We have connectors on both ends. So we have one connectors here. We have one connectors. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 connectors. So basically, for these 10 sections of fiber optics cable, we are having 11 connectors. So there should be 11 connectors that need to be used in our system. Okay, so need to be very clear on this, and from information given that the loss for every connectors is 2 dB. So 2 dB loss per connectors. So these are the informations from the questions. Okay, so let us proceed with this solution, whether you want to choose for the pin or you want to choose for the APD. Yeah, so you have to use both. Yeah, you have to test for both receivers. Let's say for the first one, we go for the pin. Yeah, we go for the pin photodiode. Yeah, so for the pin photodiode, from the equations, we have a PTX. Yeah, PTX equals to the PRX. Yeah, plus the channel loss plus the system margin, okay, and plus the DL, yeah, dispersion loss. And from this information, from the questions, we don't have any information of dispersion loss, so we can ignore the dispersion loss. We just put here that the DL is 0, so we can ignore the DL. Okay, so I just ignore the DL. Okay, so from here we can have that really disturbing. Yeah, not sure why. Really disturbing this line. Okay, please be patient. Yeah. Okay, so we have a PTX minus the PRX shall be then equals to the channel loss. Yeah, channel loss plus the system margin. Okay, so we have that the PTX is a 0 dBm for the pin photodiode. I mean, for your laser diode just now, yeah, it's a 0 dBm. Yeah, so we have a 0 dBm value there. So straight away use a 0 dBm. So we have a 0 dBm for the transmitter minus the receiver value, which is negative 45 dBm, yeah, for the pin photodiode. And for channel loss, we have a 4 dB per kilometer. Yeah, this is the attenuation of your fiber multiplied with the length, which is planned to be 5 kilometers. Yeah, 5 kilometers length of fiber optics. Yeah, given the questions. For the connectors loss, we have 11 connectors multiplied with a loss of 2 dB per connectors. Okay, sorry, not okay, 2 connectors plus your system margin is unknown. Yeah, is there any system margin given? Sorry. Okay, we have a system margin of 6 dB. Yeah, 6 dB. Yeah. So let's say we have a 6 dB there. Yeah, just to put a 6 dB. So what we have to do now is that we have to compare left and right. Yeah, compare left and right. So if we go for the left-hand side, the value will be 45 dB. Yeah, the difference between the transmit power and receive power is 45 dB. And for the right-hand side, we have the value of the summations here will be 4 times 5 will be 20 dB plus 22 dB plus 6 dB. So end up we're going to have what? 42 plus 6 will be 48. Okay, so it means that for the right hand side, the value is 48 dB. Yeah, the value is 48 dB, but the difference between the transmit and receive power is 45 dB, which means that the right hand side, which include the channel loss and the system margin, which is 48 dB, and the value of 48 dB is higher as compared to the allowed, yeah, as compared to the allowed difference between the transmit power and receive power. The difference of 3 dB, yeah. So I repeat again, if we base on this example, we have for the right hand side, the value of the channel loss plus the system margin is 3 dB higher as compared to the difference of the transmit power and receive power. So when we have this case, yeah, in which the channel loss is higher than the allowed power between the receiver and transmitter, we can see that this system is not reliable. Yeah, the system is not reliable. Okay, it's not reliable. I can see the word to be used is not reliable. Yeah, because from the calculation, we have obtained that the channel loss and the system margin value is higher as compared to the difference between the transmit power and receive power. So this system, I mean the pin photodiode cannot be used as your receiver. Yeah, the pin photodiode cannot be used as your receiver because of this argument just now. Yeah. Okay, so sorry. So let us proceed with the APD to see whether the APD will satisfy these values. Let's proceed. Yeah, we need to erase this first. Sorry for that. Okay, let's have a look for the case of APD, okay, or for the avalanche photodiode. Okay, for the APD, okay, we have a, again, laser diode use is 0 dBm, so 0 minus, okay, the line keep on coming out. I'm not sure why. Okay, yeah. So we have a PTX, yeah, equals to the PRX plus the channel loss plus the system margin. Okay, so we have a the PRX can be brought to the left hand side. So we have for PTX is 0 dBm just now, so 0 dBm minus for the receive power of the APD, I mean the sensitivity to APD is negative 56 dBm as given in the question. So negative 56 dBm is the sensitivity of the APD. Okay, so this is in dBm, yeah, yeah, in dBm. Okay, and equals to the channel loss. So we have 4 dB, yeah, 4 dB per km, the attenuation for the fiber times 5 kilometers, okay, plus 11 connectors multiplied with 2 dB per connector loss, yeah, 2 dB per connectors, okay, plus 6 dB for the system margin. So we go for left hand side first. So left hand side, the value will be equals to 56 dB. Okay, whereas for the right hand side, yeah, right hand side, the value is equals to 20 plus 22 plus 6, yeah, 20 plus 22 plus 6, so that will give us about 48 dB. Okay, so from here, we can see that the channel loss plus the system margin is 48 dB, whereas the allowed value, I mean the value between the transmit power and receive power is 56 dB. So which means that the value of a difference between the transmit and receive power is higher as compared to the channel loss and the system margin, which will actually indicate that your system that designed using the APD should be workable. Yeah, should be workable. Yeah, should be workable because of the argument that the channel loss and the system margin is smaller. Yeah, is smaller as compared to the difference between the transmit and receive power value. Okay, so these systems should be working properly. Yeah, working properly, and we can see that from here, the APD receiver can be used. Yeah, can be used as a receiver in this particular system design. Yeah, but the pin photodiode, from we have do just now, from we have done just now, the pin photodiode cannot be used as a receiver due to the argument that channel loss and the system margin is smaller as compared to the difference between the transmit and receive power difference. Yeah. Okay then. That should be the solution for question number 2. Okay, so let us proceed with the question number 3. This is about the single mode fiber optics. Yeah, single mode fiber optics. Operating at 1.3 micrometers, we are given that the mean power launch from laser is -3 dBm. The optical fiber loss is 0.4 dB per kilometer. The splice loss is 0.1 dB per splice. So 1 kilometer each means for every 1 kilometer, we're going to have 1 splice. Yeah, and for every splice, the loss is 0.1 dB. We have connector loss at transmitter and receiver 1 dB each. So at the transmitter, there should be 1 connector, and at the receiver, there should be another 1 connector. So there should be 2 connectors. Okay, and the mean power required at the APD, yeah, mean power required at the APD is when operating at 35 megabit per second. Yeah, the receiver sensitivity is -55 dBm, and operating at 400 megabit per second with the given BR, the sensitivity of the APD is -44 dBm. So the safety margin is 7 dB. Okay, so based on this given information, you need to, number 1, estimate the maximum possible length without repeaters when operating at 35 megabit per second. Yeah, it may be assumed that there is no dispersion penalty. So we assume there is no dispersion penalty. Yeah, that should be number 1. Number 2, maximum possible length without repeaters at 400 megabit per second. Okay, never mind. So we do it one by one. We do for the first one. We do for the first one, in which what should be the maximum link if the system operating at 35 megabit per second, in which the receiver sensitivity is -55 dBm. And then also need to find the length, yeah, maximum distance at 400 megabit per second operation for the APD with the sensitivity of -44 dBm. So basically, this question is similar to what we have done, earlier in example number 1. Okay, so we shall proceed further with the solution of this example. Okay, so for the case of 35 megabit per second, yeah, so we have a 35 megabit per second. Okay, I hope you can still understand, yeah, although we have this line here in our slide, yeah. Okay, for the first case of 35 megabit per second, again, the equation used is PTX equals to the received power plus the channel loss plus the system margin is standard equation used. Okay, so we bring the receiver power to the left hand side. So the PTX minus the PRX shall be equals to channel loss plus the system margin. Okay, so for the transmit power, the value of -3 dBm, so I just use -3, yeah. Minus for the receive power for 35 megabit per second, the sensitivity is -55 dBm, so we just use the -55 there. And for the channel loss, it is 0.4 dB per kilometer. Yeah, 0.4 dB per kilometer. Okay. Right. So we have the length of L kilometer. We just put L, yeah. We just put L kilometer because we don't know what to be the length. Yeah. Wow, it's getting worse. I think I need to install back the driver for this tab later on, yeah. Sorry for this disturbance, yeah. Got problems with the driver, I believe, yeah. Okay, 5 L kilometers here. Okay, and then we have the loss due to the splices, yeah, splices. Since we have a splice loss is 0.1 dB, so we have 0.1, yeah, 1 dB, yeah, 0.1 dB for every kilometers, yeah, for every kilometer. So since we have L kilometers, so we just need to multiply with L. Yeah, this is splice loss, yeah, 0.1 dB per splice. Yeah, and once plus for each kilometer. That's why we need to multiply the 0.1 dB with the L, and the loss of connectors is 2 dB. Yeah, because we have two connectors, input and output, and plus 7 dB as your system margin. Okay, yeah, hopefully it's clear then. So we calculate the value now. So we have 52 equals to 0.4 L plus 0.1 L plus 9. Yeah, so end up we're going to have 0.5 L equals to 43, and the length will be equals to 86 kilometers. So that should be the allowed, yeah, that should be the allowed distance, the maximum distance. Yeah, 86 kilometers. That should be the allowed distance for our system at 35 megabit per second data transmission. Yeah. Okay then. Okay, then we proceed. We continue, or we repeat this method with the 400 megabit per second. So I just reuse the same answer here. So I just change the data rate. Okay, the data rate used. So it should be now equals to 400 megabit per second. Yeah, 400 megabit per second. Okay, and the changes will be only on the receive power. Nothing much changes. Yeah, nothing much change on that. So receive power will be now changed to minus 44 dB. Okay, I change it to negative 44 dBm. Yeah, 44 dBm. So that should be the case. The rest will be the same. Yeah, the rest will be the same. No changes on the right hand side. Only on the receive power will be changed. So that will result on your this value will be changed also. Right, so you're supposed to get the value of your the difference between the transmit and receive power will now equals to 41. Yeah, 41. Yeah, 41 dB, the difference between them. And this is 0.4. Okay, so end up going to have a 0.5 L will be equals to 32. Okay, so end up the L shall be equals to 64 kilometers. Okay, so previously for the case of 35 megabit per second, you have a 86 kilometers. Yeah, for 35 megabit per second just now, you have the length of 86 kilometers. And for the 400 megabit per second, the distance is reduced now to 64 kilometers. So basically, this is related to the receive power value, yeah, the sensitivity of the receiver that will actually influence the length distance, yeah. Okay then. Hopefully you understand, yeah, this concept on the calculation of the length or the distance. And number 3, reduction of maximum possible link in B if dispersion equalization penalty of 1.5 dB is considered. This is the third question, yeah. Yeah, I repeat again, reduction of maximum possible link in B if dispersion equalization penalty of 1.5 dB is considered. Okay, now for this particular case, we are using the same answer, but I add with a DL now. Yeah, DL. So instead of just MA, I have the inclusion of the DL or your dispersion loss. Okay. So and given that dispersion loss is 1.5 dB. Okay, so I have to add 1.5 dB here as the dispersion equalization loss, and that will give us Okay, that will give us this loss of equals to 10.5, yeah, instead of 9. Okay, so we're going to have 10.5 dB here. Yeah, 10.5 dB. I'm very sorry about this, yeah, 10.5 dB. Okay, So, and up, we're going to have the value of 30.5 instead of 32 on the right hand side. Yeah. So that will give us the 30.5. Okay. This will give us 30.5. So what should be the value of the length after we introduce the dispersion equalization? So end up when we calculate the ratio between 30.5 and 0.5. Okay, so the answer for the length that is allowed, it will be equals to 61 kilometers. Yeah, 30.5 divided by 0.5 will give us 61 kilometers. So before this, if you don't have any dispersion equalization, the distance allowed is 64 kilometers. And once we introduce the dispersion equalization of 1.5 dB in our system, the results will be the distance has been now reduced to 61 kilometers, in which it will be a reduction of 3 kilometers of transmission distance. Yeah. Okay, so which means that when we introduce the dispersion equalization penalty in our system, the distance, the allowed transmission distance will be further reduced. Yeah. Okay then, any question for this example before we proceed with the last example for today's lecture? Any questions so far? No?
No, doctor.
No, yeah, I hope you're still with me. So only Sarvin reply to my question. I hope the others still there. Okay, so is it Sarvin or Vignesh Warren?
Serving, doctor.
Sarvin, yeah, okay. Vignesh, are you still in?
Yes, doctor.
Oh, okay, good to hear your voice then, yeah. Okay then, the last example for today. We are given the optical link that was designed to transmit data at a rate of 20 megabit per second using the RZ coding. Okay, the length of the link is 7 kilometers, and you are using the LED at 0.85 micrometer as your source. Yeah. The channel used is green fiber with the 50 micrometer core and attenuation of 2.6 dB per kilometer. Okay. So the cable requires splicing every kilometer with a loss of 0.5 dB per splice. The connector used for the system has a loss of 1.5 dB per connectors. The power launched into the fiber is 100 microwatt. The minimum power required at the receiver is negative 41 dBm to give BER of 10 power negative 10. Okay, so that is the receiver sensitivity, negative 41 dBm to give bit at a rate of 10 power negative 10. So safety margin is introduced, given safety margin of 6 dB. Okay. So the question is, show by suitable method that the choice of component is suitable for the link. Okay, so you have to testify. Yeah, we have to testify by calculation that this particular selection of a system components will work effectively or will work without any problems. Yeah. Okay, so we know that from this given information, the length is 7 kilometers. 7 kilometers length. Yeah. The attenuation is 2.6 dB per kilometers. I can say the loss, the splicing is the loss of a splice is 0.5 dB per kilometer, and each kilometer will need one splice. Yeah? The cable requires splicing every splice, every kilometer will need one splice, and every splice will incur 0.5 dB loss. Yeah. So the connector used for the system has a loss of 1.5 dB per connector. So we have two connectors, one for input, one for output. So that should be two connectors. So the loss will be 3 dB lah, yeah, 3 dB. Okay, the launch power into the fiber is 100 microwatt. So let us detail it out here. So there is the transmit power will be 100 microwatt given in watt. So we need to calculate in dB. So it should be in dBm. Yeah? So 10 log of 100 microwatt divided by 1 milliwatt, because in dBm, right? Yeah, so the answer will be equals to about what should be the answer for that? Yeah, 100 micro divided by 1 milli, so it's about let me calculate this one first. So it's about -10. Yeah, -10 dBm. So that should be the value of the transmit power in dBm. Yeah, the receive power. Yeah, the receive power is equals to -41 dBm as given in the questions. Okay, so that should be the information given. Okay, so basically the difference between the transmit power and receive power will be, yeah, if I can write it for you here, the power transmit minus the power received shall be equals to, again, the things come out. Okay, the value for this difference between transmit power and receive power should be equals to -10 minus -41, and this will give us about 31 dB. Yeah, 31 dB. I see. Sorry about this. Okay, so that should be 31 dB difference, yeah, between the transmit power and your receive power. Okay, so let us proceed with the calculation of the incurred loss in your system. Okay, so the incurred loss in your system will be comprising of few components. The first one is due to the fiber itself, which is 2.6 dB per kilometer loss of the fiber, multiplied with the length of the fiber, which is 7 kilometers. Okay, plus the loss incurred due to your splice. We have 0.5 dB loss. Yeah, so since we have 7 kilometers distance, yeah, so this splice for every kilometer, so we have 7 kilometers, so we're going to have times 7. That should be the loss incurred by the splice, yeah, by the splices. We have a plus with the loss due to connectors, 1.5 times 2. Sorry, yeah, times 2. Wow, it's getting worse, lah. What is this? (1.5 times 2). Right, and plus your system margin, which is equals to, let me check what is system margin value, 6 dB, yeah? So plus the 6 dB of system margin. So end up the loss incurred together with system margin will be equals to 42, 18.2, yeah, or 18.2 dB plus 0.5 times 7 will be 3.5 dB plus 3 plus 6. Yeah, plus 6. Yeah, so that should be the loss incurred. So end up we're going to have, this should be including the system margin. Yeah, so end up we're going to have the value will be 30.7 dB. Okay, so that should be the value of the loss incurred together with the system margin. And we compare this previously with the difference between the transmit power and receive power, which is 31 dB. So which means that the value difference between the transmit power and receive power, which is 31 dB, is bigger as compared to the loss value and the system margin. So which means that for this particular case, the system can work properly. Yeah, the system can work properly, and the component used can functions properly. Yeah. So that should be the answer for that. So the systems should work effectively, yeah, based on the components provided in the given specification. Yeah. Okay then. Is there any question for this example? So basically what we did here is we are comparing the left and right hand side. The left hand side will be the value, the difference between the transmit power and receive power. and the right-hand side will be the component that incurred loss to the system together with the system margin that need to be considered in your calculation. So based on that, we come out that we have proved that the value of the difference between transmit and receive power is bigger as compared to the value of the incurred loss. Yeah. So for this, we can say that the system is said to work properly. Yeah. Okay. So I think that's all for this lecture 11, lecture 11 part 1 on the power budget analysis. Okay. Hopefully you understand well on this topic. Okay, and next week, which will be the final lecture for our syllabus, for our course, next week, we're going to proceed with the part 2 of lecture 11, which will be covering topics of lifetime budget analysis. Okay, is there any question on these lectures for today? No question at all?
Yep.
Okay, if there is no question, I think we can stop the class. Yeah, we can end the class now. Okay, we can end the class now.